So the first technical session of this workshop, the lecture will be delivered by Dr. Giang Nguyen on the topic challenges in bridging different scale in Modelling Failure of Geomaterials. Dr. Giang is currently working as an associate professor in the School of Civil Engineering at the University of Adelaide. Dr. Giang completed his creative degree from the University of Adelaide, after which he pursued a postdoc from the University of Mexico, USA, and University of Sydney, Australia. His research interests include constitutive modeling of engineering materials, computational solid mechanics, and micromechanics of periodic quasi-brittle materials. So I request Dr. Giang to please take over the session.
Thank you, everyone. Thank you, Madhu, Dr. Derek, Dr. Musmi, and my colleague, Dr. Arghya Das from IIT Campus. So it's my honor and pleasure to present my research here in your workshop. And before I start, can I make sure it's okay with the voice, my voice and the sound? Yeah, thank you. And for any issue with the sound and video, can you just let me know? I try my best, but I may miss something during the presentation, so it's my apology first for that. So I'm starting to share my screen, and I hope it will work. Yes, and so I have a 3-part presentation going from something fundamental to one thing that we've been focusing on for several years in Australia. And so let's start with something I hope that is not very hard for everyone to follow first. And so the key focus that I would like to present here is are the challenges. So say if we want to translate our fundamental understanding to something practical, there may be a lot of challenges that we have to overcome to make our fundamental research practical. So that is the key things behind the presentation. So I would go first with something that probably easy for everyone to follow. So my background here, probably you heard from Dr. Musmi or from Madhu already. So I spent the last, let's try this one. Yeah, I spent the last 9 years in the School of Civil, Environmental and Mining Engineering at the University of Adelaide, but I have spent time at Sydney, where I met first time Dr. Arghya Das. And before that, I was in the US doing working as a postdoc researcher. So I got my PhD earlier in the UK in 2005, before my master and bachelor degree. So first thing, I try to make things a bit diluted in a very loose sense. As you can see here, I try to make some green color here for some interpretation of what is behind the technical bit. So our goal is to link the behavior at different scales. Say we are geotechnical engineer, we know sand, they have lots of grains, but the collective behavior of all grains will constitute the behavior, macro behavior of the granular structure. So it's like we as individuals constitute the behavior of the department or the school. So I want to use that as an example to make things maybe easier in concept for all of us to follow. Okay. So in order to do that, we need to know the behavior at different level, different scale, from individual to groups, like a grain to a macro continuum scale. And we established links at different scales, linking behavior of one grant to a group of grants, and so on. And with that, we might be able to predict something. Okay, so that is the thing I would like to address here. So now I would like to take this opportunity to introduce Adelaide as well, but in a more or less bit more technical way. So we have different scale. We are here in Australia, and if you look at Adelaide, this is our sort of Adelaide and the surrounding regions, and this is the Adelaide CBD. If we go to the university, so this is the like more or less the small square here is the main campus of the University of Adelaide. And if we look at the University of Adelaide, and where is engineering? So engineering is in this small quarter of that square. And our civil engineering here is mostly in this building. Of course, we share the facility and building with another school as well. We go to the entrance, we have this, but the question here, do we want to go further to a lower scale, like a lecture hall, laboratory, office, or and so on? So the answer is not really always explicit, because it depends a lot on what we want to do. But let's try first to see something like in order to get an understanding of something. At least we try something first. Okay, so I want to try to see if like a granular material or in geotechnical engineering, if we can map the behavior of one grain to the macro behavior. So it's similar to having the behavior of all academics and predicting the behavior of the department in the green color here. So why we pick GRAN? Because we are doing geotechnical engineering, and even wider than geotechnical engineering, geomechanics, we have the GRAN as the underlying structure of many things. Sand, you can see here, sandstone. If we zoom in, we see the GRAN structure. And the same thing with even hard rock, like granite in this case. The bottom line in this case, or the low scale, not the lowest, the lower scale in this case is also GRAN. If you move to metal, you can also see the GRAN structure. So whether we can link the behavior of the individual GRANs here with the group is still a question. It's still challenging. So I'm not going to solve everything. I'm just giving you a few examples to show you the challenges. Okay, so like assuming we know something here, the GRAN behavior, we have GRANs in contact with friction. Assuming we know the contact forces, we know the relative displacements between the GRANs, and say some extent contact surfaces. So between two GRANs, we have friction, and we have the rules, simplest rules like Coulomb friction. Written in this form, as you can see here. From all these things, can we make a link with the group of GRANs in this case? So that is the process called homogenization, and there are lots of approaches to homogenize individual GRANs behaviors to constitute the macro behavior of a group of GRANs. So that is a process called homogenization, or mapping something here to something there at the macro scale, where we have only macro stress, macro strength in incremental form. So it's like making a rule to translate or to predict the behavior or performance of a department based on the behavior of individual. So in loose sense, it's like that, and there may be different ways, different challenges as well. So it's I'm sorry, any questions?
Sorry, there is no side. Someone might have disturbance.
May I ask someone all to please mute your mic?
Yeah, sorry. Yeah, I thought
Saheb Handor.
I thought there are questions. That's why I stopped. That's okay.
No, there are no questions, sir. Actually, there is some disturbance. Someone must have joined just now.
Yeah, thank you. So if you are finding is difficult to sort of when you read or you look at the symbols here, index notation. My suggestion here is to look at this as a whole. So this is something we want to, the rule or something like that we want to make here to predict the behavior of a group of grants or department from based on individual behavior. So that is everything behind what I want to convey here. Okay. So we have to make a few assumptions here that I wouldn't go into the details. Say individual, in this case, it should be rounded somehow, like a spherical range, for example. Okay, and the group should be big enough because we're dealing with continuum behavior. We are not looking at individual grant in the end. We look at group of grants, and group of grants should be big enough, meaning containing an adequate number of grants to make the behavior like a continuum behavior. So, but you may ask why homogenization? So this is just something I put up to explain in a very loose sense again. So my background somehow is also solid mechanics. So I learned something about homogenization and effective elastic property of composites. As you can see here, if we crack a composite material, you wouldn't see much change it until, change it in the location of the grains, in the rearrangement of the grains, or the inclusion in this case, until it is fully broken. So that is the difference. But in composites or in solid mechanics, there have been a lot of approaches to predict the effective elastic properties, elastic mostly, because it felt very certain in this case. And these approaches are really rigorous mathematically. But if we move to more or less geotechnical engineering, as you can see here, I extracted a video from our collaborative work with Professor Bui at Monash. And you can see here, the grains are displacing or moving a lot. So that the configuration is always changing. And in loose sense, our individual needs and capacities are always evolving with time. Okay, but when it's entered the nonlinear phase, most of our efforts, or 80% of our efforts, will lead to some little significant, little gain. In this case, that is the case of nonlinear behavior compared to elastic behavior. And as you can see here, the structure is evolving a lot compared to the case of composite here. So that is the challenges in modeling geotechnical behavior or soil behavior in this case. And in the end, it's like, to me, like a balance between something rigor and the usefulness at the end. If we go all the way to make things rigorous, we may not be able to translate or to make something practical for large scale application at the end. So it's a balance. That's what I want to address here. So first thing is very simple thing, from individual grant to continuum, like our individual academic behavior and department performance. So the technical term here, you can work out using the reference later. Okay, so this is called lower bound or Roche approach. So the case here is that we assume something first. Say the contact force can be linked to the macro stress using this relationship. So assuming something, can we get something? That's something we should get in the end, is the stress-strain relationship at the continuum scale. Okay, but we cannot do, as an engineer, we cannot do things arbitrary. We need to maintain something a bit rigorous. So the rigor in this case is the work balance. So the work that all of us generate should be sum up to get something at the end at the macro scale. That's left hand side here, and the right hand side is the average work, complementary work at the contact level. Okay, so if we use that, we can work out the relationship between the displacement, between relative displacement between two grains and the macro strength. I skip all the details here just to make things faster, but The message here is the challenge. Okay. So if we do that, doing substitution, we get something here. The link between macro strength and displacement or relative displacement between grains, summing up in a loose end, average, volume average. So now we have the link between macro stress and contact grain, the macro strain and the relative displacement. We have the behavior of one grain, of one contact in this case. Can we predict the macro stress strain behavior? So in this case, we have to assume something. We have to assume there's no change in the contact. That means if two grains are like this, the contact is normal to the surface of the grain. It is fixed there. It won't change. So that is the underlying assumption. It's limited, but let's see how it works. Okay. So if we do that, we do substitution. I skip the details here just to cover the message. Okay. We in the end get a link, as you can see here, the macro strain and macro stress, and we can rearrange this in our usual way or our preferred way. In this case, we have the compliance matrix that is linking macro strain increment with macro stress increment. Okay, I won't cover the computational effects here, but it's usually easy to write things in matrix vector to get something easy for implementation later. So now, if we have this, we can get to sum up. If we assume this, we use energy principle, we get the strain link between macro strain and displacement, relative displacement between two grains under in contact with each other. We get the prediction of the macro stress, macro strain, the relationship that has the behavior at the grain scale or individual behavior in this case. K here the stiffness, and L here the branch vector. That is basically for spherical grains, the normal to the contact. But the underlying physics here is that to do that, we have assumed something. And that assumption, if we put in 1D case, would look like this. So the grains, they all should be lining up that way to make our assumption valid. So in this loose end, it's equivalent to a system of springs in zero springs. And we put that way, we do that kind of homogenization, we get the stiffness of the system that is smaller than the reality, the real stiffness. So in other words, we have implied some rule here, and that rule leads to something different from reality. So that is the case here. That is the implications of the assumption we had here, and the end result is just valid for one particular case, as you can see here. So it's like we are not the same, but if we are forced to work or to have a structure like this, our performance will be something under predicting the real performance of the department. So that is in loose sense, it's like that. So there, you've seen what is called the lower bound approach. There must be something called upper bound approach. I will go quickly through here, but the difference is instead of looking at link between stress, macro stress, and contact force, we are assuming something here. The link between relative displacement and macro strain through the branch vector, or for spherical case grains, that is the normal vector to the contact. Okay, so from this, we still need to maintain the energy balance, because that is something we need to focus on. We cannot make a arbitrary assumption that from this we get something. We need to stick to the rule. The rule here in loose end is the energy balance. Okay, if we stick to the rule, we work out the link between the stress and contact force. So this is the relationship that has been widely used in discrete element method. So now we have the links, displacement with strength, stress with contact force, and the behavior of individual contact. We do the mapping or homogenization in the similar way. Okay, assuming no evolution of contact, we use all relationship here. Doing substitution, we get in the end the relationship between macro stress and macro strength that takes into account the contact behavior and some geometrical properties as well. And again, this is a particular case of strand rearrangement. In 1D, it's like that because we assume the strand in loose sense or the displacement in loose sense is linking directly with the macro strand that way. So in 1D case, it looks like this. And the result in this case is stiffer than the real behavior of the granular system. That means it overestimates the performance of the department if we assume all our academics are working that way in that structure. Okay, I skip the details here for the enhancement, but I leave the very useful work here by Professor Giang, Hichen, Misha, and so on. So we learn with Professor Musmi, we learn from this very useful work. So again, this is just another rule that is working well in one case, but not another. Okay. So with Dr. Musmi, we learn through different things and we try different ways. So in loose sense, say we're not looking at individual grants, but we have to look at the groups of grants because the group of grants, like we are in different groups, geotechnical, we have different criteria, different things than structure or environmental. So we need a stepping stone between individual and the department. That middle ground or middle scale here is, say, in loose sense, the discipline. So we cannot map individual behavior directly to department response. It's very hard because we have different discipline. That discipline in this case is our group of grants. Okay, so if we do that, I skip the details here. I'm sorry, just to give you a test of the challenges and the way we can go around to tackle the challenges. Okay. So if we do that, we end up having something useful. So this is our the result of our research with Dr. Musumi. We haven't checked all the results yet, but as you can see here, there might be several different ways to map the grants behavior. So K and KS are the stiffness of the contact, and E and nu. Basically, we are engineer. We know E is the anomalous, nu is Poisson ratio. So these are the link between the contact behavior and the macro behavior. And we sum up our research. We got 8 different cases. But the problem here is that we work out all these results from some assumption. The underlying assumption is that there's no evolution of contact, and that is one of the key things. But our reality here is very different. The contact we assume here is spherical, elastic, but in reality, it's not that. Everything is evolving, so it's really challenging. So it's like our department. We have different groups, and in each groups, we have different academics, students as well. They are following different sort of discipline. The performance are also different. There's no one size that can fit all here. It's very hard. So that is the challenge in mapping something, say academic to discipline and department. It's very challenging. Okay, but the reality is that we still have to do something. Regardless of how challenged I say we are engineer, we have to predict something in the end using whatever tools or approaches we have. That's the must. We are different from scientists who are making something, discovering something, but for our case, we have to predict something using whatever we have. So that is one of the challenges as well. Okay, so I give you a test of an example here of the challenges. Say we have siêu thị sản, say different academics, different level, and so on, different performance, different disciplines. And for this case, siêu thị sản, they have very large discrepancy between the size of the silt grains and the bigger sand grains. So it's very hard to model everything. So we have to make some simplification here, that our contact in this case contains the behavior of silt. So that is our assumption. And we take into account the coarse phases only. So that's another challenge. We cannot take care of all individual students. We have to divide, to make groups and treat the groups separately in order to make something practical at the end. So that is the loose things behind the technical fundamental challenges here. So in order to do that, we need to make a rule. Our rule here is something that I have presented, the lower bound, the upper bound approaches. I might be messing up these two things, but these are the rules that we have been set. It's just valid for some configuration. We stick with that rule, we use it, even though we know that it's not correct. Okay. And now from the rules we established earlier, we set out the criteria for individual performance. So our individual performance here, we have two grains in contact with each other, two big sand grains. In between is the silt grains. So we need to establish something that is sort of making sense for the behavior at the contact here that includes the silt grains as well. So I skip all the details. It just shows you the performance at the end. It's like we're predicting the performance of the department based on something we set out for the individual. Okay, so these are the model prediction. You may not need to follow all the details. So we do two cases for RAN and unRAN behavior, and you can see the macro responses here. But what we want to show is, which is to us more important, is the behavior, or this is the mechanism behind the responses. So all the macro responses here, like the department performance, are underpinned by the grain response here and the distribution of contact in different cases with different silt content, 0 to 30%. And that can cover both, say, the underlying mechanism has been encapsulated in the model to give the model macro prediction that is close to reality. Not perfect, but close enough. And underlying, we see the change in the contact forces evolution at different times. So that is reflecting our individual capacity and behavior evolving with time, and all these things constitute the behavior, macro behavior, or behavior of the department. Okay, so I make some conclusion here and move on to the next one. I hope I won't run out of time. So say this is challenging, but it is beneficial as well. So if we do it in a traditional way, we set up a rule, we look at the macro behavior only, we may be able to do something good, but in the long run, it might not be easy because we lose the contact with the individual. We lose things at the grand scale. Okay, so we include the grain. It is grain contact into our computational model. Is very time consuming because we have to track individual grains. It's like tracking the behavior performance of an individual in the department. Okay, and it's hard to establish link between grain and macro behavior. But the benefits here is for the long run. If we make the rule correct, we will be able to predict something. So that is for the long run, it would be beneficial. Say if we have better computer in 5-10 years, that will help us overcome the challenges here. Okay, so when we want to do curve fitting is a rule that you apply. Sometimes it works well, but many times they are not working well. Okay, so if we manage to establish a platform that makes everyone happy, so it's beneficial in the long run. Okay, and in geotechnical engineering, we usually use mixture theory, but the kind of homogenization here using different approaches, we give us something better than the mixture theory. Okay. So overall, it's also depends on our choice. We can go with this kind of approach, looking at the grand scale behavior to predict the macro scale, or we go with our traditional way, more classical, imposing some rule at the macro scale and ask the model to predict something. So it's all up to us, because it's better to have more tools and models than less, okay, for different jobs. So this is just a test of the challenges from the grand scale. But if we look at the test, as you can see here, is our test run by one of our postdocs at Monash with Professor Ha Bui. And you can see here, say, the behavior in this case is localized on a thin or on a narrow zone here. It's like we have in a department a big dominant group that is perform much better than the rest. Okay, so I conceptualize this like this. Okay, so outside this band we have something. The shear band here is the dominant one. Behavior of the macro behavior here is, I mean, the inelastic behavior is dominated by things that happens in this red band, shear band in this case, you can call it. The macro behavior is the average one of both zones, band and the zone outside it. So if we're doing the mapping, so what do? We map everything to this zone, the red one, the outside, or the macro one. Say which group we will go with, okay, in the loose sense. So this will open something for the next part of the presentation. So that is really important, because if we miss something here that is dominating the macro behavior, all we are doing for the mapping might be totally incorrect. So that is the last sentence here. If we have one big group performing very well, we don't distribute equally or accordingly the resources to that group, that is something wrong. Okay. And I will open the next part here. I think it's short enough to give you a brief idea about localization. Before we try something that can help resolve some conflict here, okay? So as an engineer, either structural, geotechnical, we usually go to the lab. We have to learn it, we test it, we break a specimen. So the specimen I want to present here, I would like to present here is, say, for structural engineering. We have a dog-bone specimen. We put it in tension. We break it. We tension it until it breaks. And then we record something. We work out stress strain. Okay. So, but what is wrong here? Because in the end, you see the development here. You see that it is getting, it is cracking, fracture at a specific structure. Okay. So we run the test, we get the load and extension. So normally from the load and extension, we can work out the stress strain curve for our model calibration, okay, and so on. But what's wrong here? So if we plot the strain distribution at different stages of loading from 1 to 5 here, we see something very clear here. Before point 3, you can see here, the deformation looks really homogeneous. So it's almost same everywhere. But beyond it, we would see something very localized. That's the red zone here that in the end fractures. Okay. And if we plot, sorry, yeah. If we plot the strain distribution along the vertical line, you can see here at 1, that's relatively all right, not much. It's fluctuation because of the intrinsic inhomogeneity of the material. 2, 3 is roughly similar, but from beyond 3, upon 3 here, roughly the peak, we see one zone here in the middle starts to develop very high intensive strength. Okay, so in this case, the question here is what we are doing here. Are we dividing everything by the gauge length to get the strain and dividing everything by the cross section to get the stress? Is that correct? The question here is no, because we are transforming the behavior. In this case, or the material of the specimen is transforming its behavior from material in loose sense, when everything is the same, homogeneous everywhere, to a structural or a boundary value problem due to the localization. Okay, so that is something we keep in mind first. And if we plot the strength at different location or at different area, so the global strength here, sorry, the global strength, that is macro average strength, the sort of light blue curve here, and the strength in the localization zone, the zone where it where cracking in the end happens, we see something different here. We plot the strength evolution with time. So we see the departure of these two strengths. At this point, it's called bifurcation point. So still, we have the question, can we use the average strength here? I will try to answer later. Okay, so yielding in this case will lead to homogeneous deformation, but after being localized, the problem would become much more complicated. Okay, it becomes a structural or boundary value problem. We do the same thing if we run tests for geomechanics, rock in this case. We do this, we record it, we plot the strand. You can see the strand evolution and intensive deformation strand here, very high in a zone that in the end leads to cracking, failure of the specimen. We do the same thing, we plot the strand profile. We see that really after peaks on C here, the strand tends to intensify in the narrow zone here, and it's in this case 1 order of magnitude when it's close to fracture, shear fracture at the end, compared to the strand outside the red zone here. Okay, we can do the same thing to identify when that kind of bifurcation, keep in mind bifurcation of the deformation take place, when we plot the strand in 3 different regions, inside, outside, and the macro strand. So still, we put the question here, can the average strand be used or not? We try to answer that later. So the last example here is geotechnical engineering. As you can see here, you've seen the video earlier. We do the same thing here. We try to, in this case, homogenize things inside the band and outside the band. Okay, or we put 2 big zones inside that band and outside that band. We work out 3 different behaviors. So now it is sort of not easy. What behaviors we should follow? Say the macro one, the one in the middle, like the department behavior. The dominant group in this case is a green one, as you can see here. It is deforming a lot. The rest, not much deformation. This is going down that way. So which behavior as an engineer we should take to calibrate, develop a model? Okay, so I give an example 1D first to have more fundamentals inside. So if we tension the bar like that, it cracks there. We put H as the gauge length, because in the end we need to work out strength from displacement. Okay, we tension it, it crack in the middle. So because of the equilibrium, when the stress is or force is starting to reduce, it's 1D equilibrium. The stress of force outside and inside the band, the zone here, the red zone here, should be the same. Okay, so if the zone here is extending, leading to fracture, the zone outside it should be shrinking, because it's not fracturing. It's still elastic. Elastic should follow the elastic unloading path. Okay, so now we are an engineer. We need to work out strength. So what should we do? Basically, we divide the displacement here by the gauge length. We get this stress strength. But if we change the gauge length, what happens? If our gauge length is increasing, we get a different response. Okay, if it is increasing, that means we record deformation over a larger area, so it is softer in this case, and we end up having this. If this keep increasing, we would get that behavior, and correspondingly, we get 3 different stress strain responses. So in this case, the answer here is that it's incorrect if we do the averaging the normal way, like an engineer usually does. Okay, because there's no unique stress strain here that we can use. The fundamental behind is, I try to explain this in using energy principle. Okay, so like you have a spring, you load the spring, so the longer the spring, the more strain energy you have. Okay, but in the end, the string will break at one specific point, regardless of how long it is. So in this sense, all the energy stored in the string will be dissipated, will be released at one specific point. And regardless of how long your string is, it will break at one specific point, and it is releasing the same amount of energy. Okay, so due to that scaling, see, the energy dissipated is scaled with the surface area, but the energy storage is scaling with the volume. So these are very different. So fracture in this case is localized, and it's happened at the weakest cross section, like a string. You break it at one specific point, that is the weakest. So in this case, if we do it the traditional way, we ignore the energy dissipation, we end up having just stress strain. They're totally incorrect. And stress strain curve in this case for post peak or post localization, everything localizing is not correct physically. Okay. So what do we do if this is incorrect? So this is a very quick example in ductile material. We need to record the energy as well, and this is the way they are they have been doing to get the energy. The energy in this case is the essential work of fracture for metal. Okay, so say I have the gauge length here. I put gauge length, change it. I change the gauge length from H1 to H6 here. I get different curves. Okay, because in this case, our curves depending on the gauge length extension here. Now, for each curve, I work out the area under each curve. Okay, for say H1 here, gauge length number 1, I had the area. For gauge length number 6, I have the area. I divide this area under the curves by the cross section area, and I plot them. I get in the end a straight line. So this is not my invention. It has been there in the community of ductile fracture for 20-30 years. And if I plot this, I get a unique thing. There's an equation behind that I wouldn't show here. I don't show here. So the line here, the slope, is the non-essential work of fracture. The work that is dissipated when under plastic deformation only. Okay, the intersection with the vertical axis here is the essential work of fracture. That means the works that is dissipated when we create fracture here at this location. So in this case, the conclusion here is that stress-strain relationships is not adequate. We need to add something else, and that something else in this case is energy dissipation, essential work of fracture. So now we go back to geomaterial. We use the same example, and we try to cut, say, we try to work out different zone, 1, 2, 3, 4, in this case, across the band. Here, we do the same thing. We get the change in the stress strain responses. And if we are geotechnical engineer, we look at volumetric behavior. We see the response is changing with changing gauge length in this case, in loose sand, because in all 3 cases, the thickness of the band remains the same. So the only thing changing is our gauge length. Our gauge length is not a material property. It's our input. We want to measure strength over that gauge length, but material is always localizing there, or the specimen is always localizing its deformation over the length h here. So that length hash is somehow the material property, at least in loose set. It's not absolutely correct, but it's a material property. So the ratio here between that band, the side of the band, and the gauge length is creating something called side effect here, because we are varying hash, but the material in this case doesn't allow us to vary anything with doesn't allow us to vary the size, the thickness of the band, because that belongs to the material. Okay, so this thing is the side effect that we have to end up with, and in this case we cannot define the stress-strain relationship in a normal way. Okay, everything is broken down in this case, so we won't go to the details in this case, but move on to something. This is really a bit more fundamental. So we try to solve the equation. Say we have stress-strain relationship with the Stockton branch. We want to implement it in a Feynman. We want to run it. And what's wrong here? Okay, something wrong here that I should try to briefly cover is the negative stiffness. There's no negative stiffness. The negative stiffness that we get in the end is our interpretation. It's totally incorrect physically. And if we try to force it to work that way, we run the dynamic simulation here of stress wave propagation with a weak element. That weak element is following that stress strain. Is in the end, is it blocking everything? Because if we learn about a bit about stress wave, we see that negative stiffness will lead to imaginary wave speed, and our system in this case is totally wrong. But we won't have time to do anything now in this very short lecture. I think I'm running out of time, so I have to try to wrap up things. So I go quickly through this. Say, if you have a model that is having some softening behavior, as you can see here, what do we do? So there are different ways to handle this thing to make things in the end working for us. We are an engineer. We need things to work at the end, regardless of how wrong that is, because in the end we need to make some prediction. So there's some practical stuff that you can try to Google to find. So I sum up 3 things here that I have first-hand experience with, but there's plenty of other similar technique, regularization techniques that can be useful as well. So the non-local one, we won't have time for that. The sorry, this is smeared crack or deformation, and the artificial viscosity. So I'll go very quickly through here. Non-local one is to make more interaction between your integration point and the integration point in the neighborhood. So that's all. We can make a model non-local easily by putting the average integral into the say the yield function or the effective plastic strength, accumulated plastic strength. So if you have this in plasticity, you can make it non-local by summing up, doing the average weighting, whatever, to get the non-local quantity that can be used to run your simulation. That might work, okay, but this should be very careful. And I put the document here to list the issue with different ways to make a model non-local. It's underlying, there's a lot of things. The smear crack is loose end is to scale the properties of the material, so that in the end, the model, our final element or our integration point with the given size is able to reproduce the dissipation energy, fracture energy, or in the loose sense that we impose in that we got from the test and imposed to a model. So that's the case. So we're scaling artificially the behavior of the model to get something at the end. It's practically it's very useful. I use that a few times as well, but if you go to large scale, it's not scaling well. Okay, scaling with large scale, very large scale, we will talk about that later, is very different and very challenging. So the last thing here that we did with Professor Das at Sydney and Professor Aina, and to make a model add some artificial viscosity here to make a rate independent model behaves like the rate dependent. So that is sensitive with the rate of loading. So this is artificial. It has very little physics there, but it's useful. It makes things work nicely with sort of minimal amount of time into the implementation. Okay, so we did something here to prove that without rate independent and with different meshes, nothing will work. Okay, no conversion as you expect from Feynman analysis, but with rate dependency added, we managed to get something useful. Although what we're doing here is artificial. Okay, so that's the issue. And the last part here is our my research with Professor Habui at Monash during the last, I think, more than 10 years. We've been working together because we have some common interest in bringing more fundamentals to the practical application. And I hope you can still follow me. I'm not making things boring. So we try to work out an approach. It's just an approach, not the best, but for us, it is something useful. So that is something we want to convey here. So the challenge here is the scales. So we go from individual to department, group, department, university, and so on. So the longer we go from individual, the further we go, the more challenging it would be. Okay, it's like bringing our fundamental of behavior to grants to very last application in the field. So in order to do that, we cannot bring everything from grand scale to very large scale. It's impossible. We don't have enough resources to do that. Like managing a big group, we need, if we go down to the level a student individual, it's really hard. It takes time and resources that may not always work. Okay, so we need something like a balance between accuracy for prediction and practicality that allows us to bring to some very large scale practical application. Okay, and we're trying to find a rule for that. If the rule is sort of balanced, it makes many of us happy, then it's good in the long run. That is in the loose sense. Okay, so now I put something many scales together from grand or individual to field scale, where the practical applications is really challenging. But what we are learning so far is at this scale, a group scale, whatever, if we are academic, moving to component scale, we can learn, we can do a lot of things because we have lots of data resources. Our lab allows us to do these things not quite easily, but at least manageable. And if we have good computing resources, we can run direct numerical simulation, like DM in this case, by Professor Habui and his group. And we can see a lot at the grand scale, individual scale in this case, or something in between, mesoscale we call it, for the localization band. But we shouldn't forget one thing. All what we are doing here is for one purpose, predicting something. So I put here the challenges in one of our project here, block caving. So the scale here is kilometer scale. So whether we want to model this at field scale, kilometer scale, from our understanding at the component scale here, and more or less the grand scale, if possible. Okay, so we're here at the group. I need to check my computer. It's getting slow, so I hope it's should not be crashing. Yeah, I'm sorry for that. It's sometimes it crashed in the middle. Okay, yeah. Okay, I've tried now. Okay, so we are here as a group. We want to predict something at the large scale. If we go too far too quick, we might lose connection with the other end. And sorry. Yes, if we want to bring everything from the lower scale here to the large scales, it might not be possible because it takes a lot of time and computing resources as well. So the challenge is usually the prediction. So we learn from the lab scale, component scale, we have data, but going to prediction, we usually do not have much data. Okay, so like we have individual capacity here given. We have the department structure. So this is, you can read this very interesting paper on fracture challenge. Okay, so they are given these individual sort of behavior from steel testing, like our individual behavior. They're given the structure here with loading, and they ask the competitors to predict the responses, blinding them from the experimental data. Experimental data here were performed, obtained from two groups in dark and gray color here. So you see 12 teams or more than 12 teams here, or 12 teams. They have 13 teams, I can see here, have different, very different prediction. So this shows the challenge from knowing something here, individual capacity and department structure, to work out the performance of the department. Okay, it's very challenging. If we want to go to an extreme, so this is my work long time ago at the University of New Mexico, where we have to predict the fracture of ice in the Arctic at a very large scale. So say 1,000 kilometer scale. So in this case, our element size is 10 kilometer. So with 10 kilometer, nothing we can do. We cannot bring the size of 1 gram, maybe meter into the equation. Okay, so that leads to a few things here. My conclusion that was sort of useful for my research direction after finishing my job at the University of New Mexico. That scaling is not the normal way. Scaling using sphere crack is not useful. It's not working well. We can enhance the model using advanced technique. You can hear a lot about phase field, multi-scale modeling, but it will never work here, I believe. Okay, because it takes a lot of time and resources at the large scale. We never get the solution if we do that. And technically, you go with the extended finite element or strong discontinuity approach, it will be challenging as well. First, the scale. Second, how to make sure we have the correct description of several intersecting cracks that is branching and propagating like that. Of course, we can do something, but I give you an example here that we did with Professor Das a long time back, and we can run simulation at the small scale here, but to give you an indication, it takes a lot of time to finish the simulation for 10 centimeter size. So that say that we won't be able to use all these things, fancy things, for the large scale. That's one conclusion. We can go with the multi-scale, like dividing and conquer. Okay, so we have one integration point. We make that integration point a multi-scale by having an RVE using DM, in this case, my college at Hong Kong University. So he did that, but when we asked him how long it take, he said a few days. And I had another chat with another college at Lyon doing similar things for FE square. As you can see here, it would take a few days for the prediction of failure of a small specimen. Okay. So now we have to develop something that has the balance. I'm sorry, I'm running out of time. And if, say, in loose sense, if our group or department is too big and it has a few dominant groups, say the localization band here, We can call it fracture possession in fracture and damage. How many bands, how many groups dominant that we can take into account in the model. We cannot go down to the individual in this case. Okay. So say knowing this capability of this group, can we work out the department response? So that's mean going from meso group to macro in the loose sense. You see the prediction here. We see the band. We can work out the evolution of the thickness of the band. Okay, it's evolving, but it's really hard to take the evolution into account. You have seen the behavior inside the band, outside, and the macro one. So now the question here is, can we link all three curves? They behave together, as you can see here. What are the relationships? Okay. We do that. Don't pay much attention to this. You can read the papers or something else later. So we use a strong discontinuous approach, but we regularize it over the width of the band to have the strength inside the band that way. That strength inside the band, the dominant group. And if we do that, we look at the configuration of a specimen like that. We have the strand red inside that red zone. The strand outside the band is blue here. The macro strand is the black one here. Okay, so we have this relationship. We would manage to sort of work out something. And the details here is too much. I leave it there for you in case you need these details for checking or for further understanding, but I will go quickly through it. So in order to establish something, we need to resolve the conflicts first. Our conflicts here is something like friction between the zone inside and outside the band, okay? Like these two, they are sliding against each other, as you can see, you have seen earlier. So we have all the links here, okay? We have the behavior inside the band, outside the band, okay? We try to link all of them, okay? Again, we have to use the work balance. That is sort of something we must follow. We cannot impose something arbitrary, okay? So if we use this thing, we work and the relationship between strengths here, we can in the end work out some rules here, okay? The stress here is still volume average, but there must be something for the interface between the band and the region outside the band. So that this one is the equilibrium condition or traction continuity across the boundary of the band. So we have these rules. We have established the kind of rules here. We can work out in the end something that linking all behavior, red, blue, with the macro behavior. I skip all the details here, okay? That requires some quite amount of time to work out it, but the key thing is to use the traction continuity here and the strength in different forms inside and outside the band, and their constitutive relationship different. So we work out in the end the link between macro stress, macro strength, taking into account the behavior inside the band, red, outside the band, and of course the volume fraction F here. Well, I skip that just for making things faster, and the orientation of the band. So the summary, we have established something from meso to macro, like from a dominant group that dominates the behavior of the department or the behavior of the macro specimen. We make the link, we use their interaction to work out the relationship here. The relationship here is explicit. That is one thing we should keep in mind. For non-local, for other things, it's implicit, so that thing makes it hard for calibration. So the relationship we have here is explicit. That means we can work out one thing from another. Say from working out macro behavior from micro behavior, from meso behavior, or if we know the meso behavior, the dominant group, we can predict the performance of the department somehow in loose sense. Okay. So you have seen this relationship linking almost everything we have, but not everything. We skip the grants behavior. The grants behavior is lumped into that D here, inside and outside the band. We don't have that here, but we have the behavior of the group of grants inside the band and the behavior of the group of grants outside the band. Okay, they are described by that D, red DI, and DO, the blue one. So now we make another question. We have established the explicit links between macro and meso, say group, dominant, and department. So now, if we know the macro responses, can we work out the meso one? It's like having a lot of resources at the department level. How we find a way to distribute nicely, effectively to different groups. Okay, knowing that one group is performing better than the rest. Okay, so I use this one, the geotechnical test, because I believe most of us here are geotechnical engineer. So we go to the lab, we run tests, we get the data, we do everything, and we know earlier that this is not correct because of localization. Okay, so the question here is from the macro test here and the information of the band, can we extract something useful? Okay, we have to assume something. Okay, so if we run tests, normally we can measure the orientation roughly. We can assume, that is the point that I would want to go further in this case. We have to assume the band thickness to make things easy. Can we work out the stress strain responses inside the band and of course outside the band? Okay, so now the question here, this is to me really important because it's been not correct in the community for a while. We do the averaging, we don't care about the mechanism of value. We end up, to my understanding, something very wrong as the material behavior. Okay, because we don't have any mechanism to track or to record the behavior, localized behavior. Okay. You can follow the slide or read the paper later. So the key things here is that if we do the averaging, you see the blue windows here. It's like that, okay, from the original shape. But the true behavior is the one that is this one, okay, as you can see. So their behavior are very different. So the stress that we usually use, they are not the macro stress, because we cannot define macro stress in this case, as I have shown you to a simple example earlier. We can only work out macro stress from the stresses inside the band and outside the band. So our interpretation is usually sigma 1, 2, 3. They are macro stress. To me, it's incorrect because as you can see here from the deformation, they are more or less the stress is outside the band. Okay. So if we accept that, we can work out something useful. Okay, that is in our recent paper. So say in the loose sense, if our way to distribute the resource department to the dominant group, in this case the red one, is usually not correct, not fair. They perform well, but they got less resources than the guy outside the band here. Okay. So if we do that, I will skip all the details. We assume elastic outside the band. We have the stresses, we have the psi, we have these things. We can work out from the macro test data. I use the X-ray data here, but actually we don't need this X-ray behavior. Okay, we don't need the X-ray strain contour. As long as we have the macro, we have the data stress and shortening of the specimen, not strength, shortening, because it's getting shorter, but there's no average strength that can be defined. The macro strengths cannot be defined correctly here, okay? And the angle of the band, we can work out something useful. That is, inside the band is following that. The macro here is usually we get in loose sense. Outside the band is that way. If we want to look at the volumetric responses, we will have 3 different curves. Okay, so now it's up to us, but truly the material intrinsic behavior, inelastic behavior that is dominating everything, dominating the behavior of the specimen, is the one inside the band. That is the green one here. This is the one we should use for the calibration of our model and for our understanding as well. Okay, so in this case, we have found a way to distribute the resources to the best group in the department. Okay, so the last few slides I will go quickly is the benefits. We have done a lot, but sometimes what we have done could be useless. So the question here, you have done a lot, Giang. What is the usefulness of your research? Okay, so now I should go quickly through. We use the approach, we have the band inserted in one particle, or say in loose end integration point, but not always correct if we say integration point. We can implement it in any numerical approaches, Feynman, SPS, or MPM with good prediction. Okay, it seems it can work well if we find a way to distribute it, to distribute the resources. So we can apply it to different disciplines. And now the other thing here I want to address is the mechanism behind the macro response. So normally we run the test, we don't care. We assume everything is homogeneous, but it's not always the case. Okay, so in this case, we can work out something with the mechanism behind. Okay, so we look at the performance when distributing the resources. Of course, what we want to know is whether it's converging. We are either structural engineer, geotechnical engineer. We want mesh conversion. We want to refine the mesh to get better solution, but we want it to converge to something. So that is the demonstration. And the other thing is, if you are familiar with the loaded angle or the third invariance in geotechnical engineering, these are the things we don't need at all. Okay, we can generate the effects of the load angle from the mechanism behind it, not having to impose something. And we can make correlation. So we extract, as you can see, the behavior of the mesoscale, the band here. We can work out a model. We can sort of even calibrate or validate that model, and we implement it in macro constitutive structure to get the prediction. Okay, we see the mechanism behind the macro responses here. Okay. Other thing is the efficiency. We have run this one. Collaboration with Professor Dat here, maybe five years ago. We run this with Abacus, but the question here is that can we beat Abacus? Okay, it took us 9 hours, but if we know the mechanism behind this thing, we can do it in a much cheaper, faster way. I skip all the details here just to give you an indication the performance. Okay. And we can manage to get something comparable, not exactly, never beat Feynman in terms of accuracy, but we beat it in terms of computational efficiency. Okay, we capture these things, the trend, but at much lower computational cost. And we go back to this. I showed you this. It took few days for multi-scale analysis, but just a few minutes if we know the mechanism behind, and we can do it correctly at more or less the material, not precisely material, but at least it is something enrichment that we can do to capture something that the finite or multi-scales take days or hours. So can we add more? So say we have the band, we have the macro RV, can we add the fiber? We can add the grains. The question, the answer is yes. We try that too with the fiber reinforced concrete. We have the macro RV here with the band in the middle in our structure. We can look at the mesoscale of the band, okay, and look at the fiber at that scale. We can insert the model of the fiber, in this case, pull out with validation. We can do validation at the mesoscale, that scale, and even structural validation. So that means in this case, we try to incorporate individual behavior to group and to department to get some useful prediction at the end. Okay. And I hope I did not run out of time. I'm sorry. So this is the conclusion. In the end, we need a balance. We have that. You have seen that, the model with an embedded zone. And we can go down to the side, the scale of the band, localization band. We add fiber. We do prediction here with more sort of controllable, more reliable results. And we can go further to the far end where we want to predict something at the field scale. So it's like working out individual, group behavior, department behavior for something that we can predict. And if we have a balance between several things, that will help us to tackle several things at the end. So with that, I thank you for your attention, and I put a note here to know that all we are doing might be totally wrong, but we'll look at the usefulness of our approaches. Okay, thank you very much.
Thank you so much, Professor. Like, it was very much interesting and useful, and it is very well required. So we were listening to you, thought not to disturb in between, so we didn't revert it back. So thank you so much, and I hope I'm audible now. We had some technical glitch in the starting. Am I audible?
I'm sorry. This is the I guess the question time.
Yeah, am I audible to you?
Sorry.
Am I audible?
Yes. That's very clear now. Yeah.
Okay,
Yeah.
thank you. Because there was some technical glitch, I was saying thank you very much, Giang, for this insightful.
Yeah. I heard everything. Yeah. Thank you very much.
Thank you.
Usme.
So this is the question hour session. So those who are having questions, please raise your hand. We will call for the names and please introduce and go ahead with the questions. Yeah, Dr. Dash, please go ahead. Thank you.
Hi, Jian. It's a very nice talk. I have a quick question regarding your first presentation.
Yes.
So in that case, you mentioned you have some sort of a assumption that those contacts should be remain there in the particles.
Mm-hmm.
Huh? But don't you think if you
let me open it?
Yeah.
The first one, I'm sorry. Yes, Agir.
Yeah, so my question is that you have some sort of an assumption that the contact should be remain there, right? I mean, the same contact between two.
Yes.
But
It's,
so don't you think that kind of assumption will, I mean, for example, in case of granular materials or soil, we see those, I mean, dilation when the particles are going away. So these kind of assumptions will, I mean, hinder those dilation processes or something, don't you think?
Yes and no. I don't have a good answer for your very good question. So I guess this is the question, right?
Yes, yes.
Yes. So we did that. We don't have any issue with dilation. It can capture things well. Because in the end, it's a fitting exercise. In the end, is it fitting? Fitting in this case is shifted to the grand scale with that constitutive relationship. So in the end, your constitutive relationship, as I shown you here, can be at the grand scale, can be modified or calibrated, so that in the end you would manage to generate good dilation macro behavior here. The only challenge that we cannot solve is the cyclic loading. If we fix the contact orientation, we wouldn't be able to capture cyclic loading correctly. That's the challenge, and we have tried somehow to make the contact evolve a little bit to capture cyclic loading. But the question about dilation or not, I think it is not the main challenge here.
Okay, thank you.
Yeah, thank you.
Any other questions from the audience, please? Yes, Dr. Dev, please go ahead.
Professor Jiang, good morning.
Yeah, good to see you, Arindam.
Yeah, it's very nice to listen to you after a long time.
Thank you very
I
much.
was very interested in listening to you talk. So I have a small question from my side. When you were talking about this bridging between the macro and the meso scale, and I was very eagerly looking into the videos which we were mentioning about whether the applied stress we can consider really as a macro stress or not.
Yes, yes.
So I just want to mention that earlier with one of my PhD students, we had carried out a lot of triaxial experiments where we had also used the on-sample transducers. So at the mid height of the sample, we had attached the vertical as well as the radial miniature transducers to measure the on-sample vertical and radial displacement. Now, I was wondering that if we had done some exercises with that, and we have some good amount of data related to those appendages which we have used on the sample specimen itself.
Yes.
Whether we can use the information from those transducers to little bit get into the topic which you were expressing about these macro and meso type of measurements.
Yes, I think it's in principle, yes, but the details is one thing I'm not sure. So we can measure strength everywhere in principle. As you can see the strength contours here from X-ray by the academics at Grenoble University. But the challenging things here is the stress, not the strength. Yes, so you can put the strain gauges or extensometer here and there to work out the strain, but you would not be able to get the stress. So what we want here is two things: stress and strain together, because we want to use something we call intrinsic material behavior for the calibration of a model. So that intrinsic behavior should include both stress and strain. So I hope I answered your question clearly.
Yes, I understood. So in our case, our stress transducer was still attached with the actuator. So we did not have any on-sample stress recording. It's only the on-sample deformation recording, I should say, what we have.
Yes.
Okay. Thank you so much. And it was very nice to hear you after a long time.
Yeah, thank you very much, Arinda.
Thank you.
Any further questions from the audience? Not from the audience. I couldn't see there is any message from the chat box also, but from this side we have a couple of questions. So I believe Madhusudan is having one.
Thank you for very nice presentation, sir, for bridging the landscape. So I have one question regarding like estimation of band thickness. How do you estimate, how quantify the band, shear band thickness? Actually? Which parameter?
Yes, that is a very good question, and that is the one of the challenges here. So I guess this is about this band thickness, right? We learned it from a college as Duke University, Professor Manolis Veviakis. How do I put his name here? I can type here. Okay, so you see my typing?
Yes, we can see.
Yes. Duke University. And the key thing behind is that you need to plot the profile of strength across the band. And I can show you here in one of my early presentation. Yes, so say here, if you run a DM experiment or any experiment that allows you to plot the evolution of strength across the band, as you can see here, then you can use the kind of fitting in loose sense. You use either I think they use the Gaussian distribution with a length parameter. So if you manage to fit this profile with some parameters of the Gaussian or some form of distribution that has a length scale, the perfect fit will give you an indication of a length associated with the fit. So if you do that for different profiles, you get the evolution of the band thickness. So that is in one of the paper by that Professor Veviakis at Duke University in geotechnic. So I hope you can record the name and Google geotechnic to see the, I think he published it this year, 2022.
Okay, so I got mine. So thank you very much.
Yeah, thank you.
Giang, in that regard only, I have a continuing question. So when we showed this plot for the thickness calculation, it was strain. Now, when we have DM simulation, we have multiple parameters. We can have an assessment over relative displacement, rotation also, strain also. So what we noticed while doing the fit, they all of these parameters may not give the exact same length of the shear band. So which one the relative displacement is more of a independent parameter rather than strain. So any observations on that? Which parameter might be a better quotient?
Yeah, you have a good and very hard question that I don't have the answer, Musumi. So I learned this recently, and most likely I think we use the strand distribution, but I haven't. If I got your question correctly, so is it a question about what quantities distribution across the band that we
Exactly.
should use?
Yeah, which quotient?
Right?
Because strain is a derived quantity where displacement is direct coming from the interparticle interaction, which you are
Yes.
consistent.
Displacement one gives you that kind of profile, as you can see here. If you, this is the X-ray result from one of my colleagues in Grenoble. So he managed to plot the displacement profile, as you can see here. The in this figure, you see that figure, displacement profile. So it shows a jump here.
Right.
Yes, but if you work out the strand from this displacement profile, you see the profile of strand, and I think we can use that to work out in a loose sense the width of the band. But maybe you're right that rotation or something related could be used as well, and I haven't done anything yet.
And the last question also from my end, if there is no other from anyone else, is that you said somewhere that inside the shear band and outside the shear band. Now, when we have to calibrate the kind of model that you are proposing, taking into account multi-scale aspect, what experimental data it has to work on? Because from experiments having within band stresses are next to impossible probably, other than like stresses will not be able to assess. Then
yes, that's a good question too. And practically, we can go with the way we show you here. I think it's in the first or second one. Yes. So this is the practical approach. Say if we are not able, or we are not able to work out the truly behavior inside the band, right? We can use the macro behavior, but we need to keep track of the size of the specimen. So if we run the test with that size, our constitutive relationship is associated after calibrated with the data we get from that specimen. Our behavior is associated with that size. So it should go with that size. And in final element, if you use a larger size, then you have to scale the constitutive behavior with the size.
right. Had some ideas. Probably we can got some ideas.
Yeah.
Some idea probably that the macro level behavior can only be mapped.
Thank you very much, Dr. Giang, for this nice question and answer session. Thank you. So,
thank you.
Thank you, Gia.